Hi everyone, my name is Yanhui, a third-year graduate student from UC Riverside. It's my pleasure to give this talk today. I'm gonna talk about the Goku simulations that we have performed for cosmological emulation and the 10-dimensional emulators for the nonlinear metapod spectrum with percent level accuracy. Here are the key takeaways of this talk. We have performed the first simulation suite covering 10 cosmological parameters, and we have built the emulator based on the simulations named GokuNEmu. It is the most powerful emulator for the nonlinear metapod spectrum to date, and we built it using T2Emus, which is a multifidelity emulation framework that we developed for neural network emulator construction. GokuNEmu has percent level accuracy and unprecedentedly high dimensional parameter space and sufficiently broad prior range for W0 and WA. Note that it is the only emulator that allows tests on recent DESI constraints. So it will be useful for analysis of future Brodmann and Euclid data. I'm gonna talk about the background of our research and the Goku simulations, the two emulators that we have built based on the simulations, and what we are going to do next, and I will recap the key takeaways in the end. As we know that the ΛCDM cosmological model can be characterized by 5 parameters for a flat universe. The parameters are the total matter density, baryon density, the Hubble parameter, the amplitude and the slope of the primordial metapod spectrum. However, there are still some puzzles in the field of cosmology, such as the nature of dark matter and dark energy. Apart from cold dark matter, there are massive neutrinos that are usually considered as hot dark matter, but we still don't know the exact fraction of massive neutrinos in dark matter. And we are not sure whether the equation of state parameter of dark energy is a constant or it evolves over time. And the Hubble tension and the SA tension, they are disagreements between the early and late universe large-scale measurements. These problems may indicate that ΛCDM doesn't describe the universe's evolution accurately. So, facing these challenges, some extensions have been proposed, like dynamical dark energy that can be characterized by 2 parameters, W0 and WA. And the second is massive neutrinos. The parameter is the total mass of all neutrino species. And the third one is the effective number of neutrinos in the early universe, NF, and also the running of the scalar spectral index, alpha S. We take into account 5 extra cosmological parameters here. To solve those problems, there are some ongoing and upcoming cosmological surveys like the Roman Space Telescope, Euclid, LSST, DESI, CSST. The Roman Space Telescope will observe about 1 billion galaxies, from which we can extract high-precision summary statistics, and that could be used to infer cosmological models. The statistic that we are focusing on in this talk is the matter-pulse spectrum. It describes how clumpy the universe is on different scales, which is also the Fourier transform of the two-point correlation function of the overall density field of the universe. Here is the projection of a cosmological simulation. For each scale delta r, we are able to compute its clumpiness. And if we compute for different scales corresponding to the different wave numbers here, we can get a matter-pulse spectrum. How do we infer cosmological models in practice? Usually, Bayesian methods are used. I'm not getting into details of a real pipeline here, but let me explain the basic idea using a simple analogy. Suppose we know a function, or we say mapping between x and y. Here, y is some quantity that we can measure, and x is the model parameter that we would like to constrain. Then, naturally, if we got the data from observation, we can infer the model. However, in practice, x and y can be vectors or functions. For example, in our case, y is the matter-pulse spectrum, and the dependence f may be very complex. How do we get the dependence? This is just the focus of this work. We want to make theoretical prediction for any given set of cosmological parameters. We will need to run an n-body simulation, but it is not plausible to use simulations directly in inference because that will be prohibitively expensive in terms of computation. What we can do is to do regression, which is also known as supervised learning. And in this context, we call it emulation. And in this way, only a few hundred simulations will be required. How do we do simulation-based emulation in practice? We firstly sample a set of distinct cosmologies in the parameter space, and then we run the corresponding simulations and extract the matter-pulse spectrum from the simulations as the output data. With the input x and output y, we train a regression model, the emulator. Then the emulator will be able to predict the matter-pulse spectrum for any given cosmological models in the parameter space. There have been some emulators with percent-level accuracy covering both dynamical dark energy and massive neutrinos, like Euclid emulator 2 and the CSST emulator. They are both 8-dimensional emulators trained on more than 100 simulations, but they don't include NF and alpha S. Another serious problem is that they don't have sufficiently wide priors for W0 and WA that would be required for future analysis considering constraints from DESI. Then let me introduce the Goku simulations. It is a 10-parameter simulation suite covering all the aforementioned extensions, the massive neutrinos, W0, WA, NF, alpha S, and it has sufficiently large prior range for the extensions. The prior ranges are much wider than EE2 and CSST. We have safely covered recent DESI constraints. And if we look at W0 and WA, the recent constraints are out of EE2 and the CSST emulator's capabilities. Goku was designed using MFBox, a multifidelity emulation framework that reduced the computational cost for simulations by 94%. And we sampled the cosmologies using sliced Latin hypercube design. Specifically, we have two Latin hypercubes, GokuW and GokuN, with wide and narrow ranges respectively. GokuN has a higher sample density in a high likelihood region. We have 1128 low fidelity simulation pairs and 36 high fidelity simulations in total. Here is a visualized high fidelity simulation and its low fidelity counterparts L1 and L2. From here, we see that the L1 simulation looks almost the same as the high fidelity simulation on large scales, while it cannot form smaller structures due to insufficient resolution. In contrast, the L2 simulation is accurate on small scales, while it cannot form larger structures due to its smaller box size. So naturally, L1 and L2 can approximate the metapulse spectrum very well on large and small scales respectively. If we see the plot on the right-hand side, we see that the dashed lines are relative differences between L2 and HF, and the dotted lines are L1 with respect to HF. We see that the low fidelity spectra are very close to the high fidelity ones, and the differences are within 1% over their dedicated scales. Based on the Goku simulations, we have trained the metapulse spectrum emulator GokuNEmu. It has 3% accuracy in the GokuW space and about 0.2% accuracy in the narrow range. However, there are some limitations of GokuNEmu. It was only trained on 6 distinct ratios because the complexity of Gaussian processes scales poorly with sample size, and we have a relatively large sample. And it covers only the overlapping K range of L1 and L2. It doesn't fully exploit the K range allowed by the simulations because it is limited by the emulation technique. Also, it is low in inference. And another problem is that the accuracy in the GokuW space is not that good. If we look back, especially on the smallest scales, in the case of GokuW, the error can reach more than 10%. We then explore neural network approaches, trying to solve the problems. We have developed the T2Mus, a novel neural network emulation framework for multifidelity emulators. And using this technique, we have built GokuNEmu based on the Goku simulations. It outperforms GokuNEmu in every aspect. It has accurate interpolation over redshift, because we have now included 34 redshift bands between redshift 0 and 3. And it has fully exploited the spatial scales allowed by Goku. From the plot below, we see that GokuNEmu has a wider K-range. In addition, GokuNEmu is orders of magnitude faster in making predictions. And we have significantly improved the generalization accuracy from, for example, in the GokuW space, the error is decreased from 3% to about 0.5%. And if we zoom in, we found that the validation error is mostly within 1%, and with only mild exceptions on the smallest scales at low redshifts. And in the future, we are going to build emulators for other statistics like the halo mass function and weak lensing power spectra. Here we recap the key takeaways. Feel free to let me know if you have any questions about this talk. Thank you for your listening.